Look at this forest. Dense, green, and seemingly timeless. It feels permanent, like it has always been here and always will be. But this landscape is not stable at all. It exists because, again and again, a volcano wiped it out. This is Mount Taranaki in New Zealand, a near-perfect cone rising above a broad coastal plain and wrapped in a ring of deep native forest. It is one of the clearest examples on Earth of how geology and ecology are locked together. A mountain that destroys its own slopes, and a forest that returns, patiently, after every catastrophe. To understand how that works, we have to start with the mountain itself. Taranaki, also known as Taranaki Maunga, or Mount Egmont, is an andesitic stratovolcano on the west coast of New Zealand's North Island. It is geologically young. Eruptions began roughly 130 to 200,000 years ago. Today, the summit stands about 2,518 meters high and is one of the most symmetrical volcanic cones in the world. That symmetry hides a complicated and unstable history. Taranaki has gone through many eruptive phases, building a cone and then partly destroying it. Over tens of thousands of years, lava flows, pyroclastic flows, debris avalanches, and lahars have spread volcanic material outwards, forming a broad apron of deposits around the mountain. Geologists call this the ring plane, not because it is a perfect circle, but because it is a roughly radial plane of overlapping volcanic deposits that surround the volcano. Some of the most dramatic events in Taranaki's history were large cone collapses, times when part of the volcanic edifice failed catastrophically, sending huge debris avalanches and lahars tens of kilometers across the surrounding landscape. Studies suggest that at least 5 major collapses have occurred in the last approximately 70,000 years, with one about 25,000 years ago, sending material beyond today's coastline. Alongside those giant failures, Taranaki has produced many more ordinary eruptions. Over the last 30,000 to 40,000 years, it has erupted well over 100 times. In the last 9,000 years, minor eruptions have occurred on average about every 90 years, with larger, more damaging eruptions roughly every 500 years. The last major eruption is usually placed around the mid-1600s, and the last smaller activity, including lava dome growth and ash emissions, occurred in the 18th and 19th centuries. Today, the volcano is quiet, but it is classed as a sleeping active volcano, with a substantial probability of erupting again in the coming centuries. Every one of those eruptions and collapses has a double effect. In the short term, it is destructive. Ash, pumice, and hot surges of gas and rock strip vegetation, bury soils, and rearrange rivers. Lahars, fast-moving mixtures of water, ash, and debris, follow river valleys down to the lowlands, scouring some areas and smothering others under fresh volcanic material. In the long term, though, these same processes create new surfaces, new topography, and, eventually, new soil. From an ecological point of view, each large eruption or lahar is a reset. In places, the disturbance is so severe that almost all organic matter is removed. What remains is bare, unstable volcanic substrate. Ash, lapilli, blocks, and boulders, with almost no nutrients and little ability to hold water. This is where primary succession begins. Primary succession is the process by which life colonizes a surface where no soil exists yet. On fresh volcanic deposits, the first colonizers are usually microscopic organisms, algae, lichens, and small mosses. Their spores arrive by wind, water, or animals. They cling to rough surfaces, tolerate intense sun and rapid drying, and begin the slow transformation of rock into soil. As they grow and die, they add tiny amounts of organic matter, trap dust, and start to stabilize the surface. As the first thin film of soil builds up, taller pioneers can establish. Herbs, grasses, and shrubs, often nitrogen-fixing species, start to put down roots, crack the substrate further, and add more biomass. They improve moisture retention and create shaded microhabitats. Over decades, they prepare the way for more demanding species, the trees that will one day form a mature forest. In Taranaki's case, the climax communities on stable, undisturbed slopes are mixed temperate rainforests, dominated by native broadleaf species and conifers such as podocarps. These trees can be slow-growing and long-lived, relying on deep, well-developed soils. Where the ring plane has been stable for centuries, you see complex, multi-layered forest with tall canopy trees, understory shrubs, ferns, epiphytes, and a rich soil fauna. Where disturbance is more recent, you see younger stands, simpler structure, and species that are better adapted to exposed, nutrient-poor conditions. Now imagine looking at all of this from space. Satellite images of Taranaki are famous because they show a striking, almost perfect circle of dark green forest, surrounded by a patchwork of pale farmland. It looks like a natural ring of forest drawn with a compass. But here, the human story matters as much as the volcanic one. That crisp circular boundary is the edge of Egmont National Park, established around the mountain in the late 19th and early 20th centuries. In 1881, surveyors literally drew a circle with a radius of about 6 miles, roughly 9.7 kilometers, around the summit to define a forest reserve. Inside that circle, native forest was largely left intact. Outside, over the following decades, settlers cleared most of the lowland forest for agriculture. The dramatic forest circle is therefore the product of conservation policy drawn on top of the pre-existing ring plane, not a perfect natural edge created by lahars alone. That does not mean the geology is irrelevant. The reason the national park boundary can be drawn as a simple circle is that Taranaki stands on a broadly radial plane of its own deposits. The smooth slopes and gentle gradients of the ring plane made it easy to survey, and the volcanic soils that blanket it are, after sufficient weathering, extremely fertile. Much of the surrounding farmland owes its productivity to the slow breakdown of those same ash and lahar deposits that once devastated the landscape. If you walk from the outer farmland into the forest, you are not just crossing a park boundary, you are stepping into a time sequence. In many parts of Taranaki and the neighboring Puakai and Kaitake ranges, studies of soils and vegetation show how forest communities change with time since the last major disturbance. Close to relatively young deposits, for example, in areas affected by 17th to 18th century eruptions, the forest tends to be younger, with smaller trees and a greater presence of pioneer species. On older terraces and higher, more stable slopes, you encounter older soils, thicker organic layers, and mature stands of podocarp broadleaf forest. It is tempting to imagine a perfect set of concentric rings, each corresponding neatly to a specific lahar or collapse event. Reality is messier. Lahars follow valleys and low points. Ashfall patterns depend on wind direction. Erosion and human activity rework the surface. The result is a mosaic, not a geometric target. But the general pattern is clear. Disturbance creates a blank slate, and over decades to centuries, ecological succession writes a new forest over it. You can think of Taranaki as a kind of very slow clock, but it is not a clock with regular ticks. There is no fixed schedule. Instead, the volcano operates on probabilities and ranges. Over tens of thousands of years, it has oscillated between building and destroying. In the last few millennia, minor eruptions recur on average about every 90 years, and more substantial ones about every 500. But those are averages derived from many events, not promises of when the next one will happen. For the forest, that uncertainty is everything. The species that dominate Taranaki's native ecosystems are those that can cope with disturbance, by resprouting, by rapidly colonizing fresh surfaces, or by persisting in refuges that escape the worst of each event. Seeds and spores arrive from surviving patches upslope, from neighboring ranges, and from pockets of vegetation that the flows missed. In that sense, the forest carries its own recovery plan within its genetics and its dispersal strategies. From a human perspective, this cycle has a double edge. On one hand, the volcanic soils of the ring plane are among the richest and most productive in New Zealand once they have weathered and accumulated organic matter. They support intensive dairying and agriculture, and the national park preserves some of the finest remaining lowland and montane forests in the country. On the other hand, the same processes that built these landscapes are still active. Future eruptions and lahars will again threaten communities, roads, bridges, and farmland on the plain. Hazard assessments rate Taranaki as a major risk for the region, with scenarios that include ashfall, lahars, and renewed sector collapse. Seen through this lens, Taranaki is not just the forest that grows from its own destruction. It is a case study in how life and geology are intertwined. Eruptions inject energy and materials into the system in sudden bursts. In the quiet intervals between, biological processes slowly build complexity and biomass, using that mineral wealth. Neither side of the cycle is the whole story. The apparent stability of the forest is temporary, and the apparent violence of the volcano is part of a longer pattern that makes that forest possible. You can even connect this, cautiously, to the broader physics of the planet. The universe as a whole tends towards higher entropy, more disorder, but local systems can develop intricate order when energy flows through them. A regenerating forest on a volcano is one of those pockets of order, using sunlight, water, and nutrients released from rock to build and rebuild structure, all while the deeper geological engine continues to churn beneath it. The forest you see today on Taranaki's slopes is therefore not a final state. It is a snapshot, one frame in a film that has been running for hundreds of thousands of years. At some point in the future, whether in decades or centuries, another eruption, lahar, or collapse will cut into these trees, bury some of them, and strip others away. For humans, that will be a disaster. For the ecosystem, it will be another reset in a long series of resets. The beauty of Taranaki lies in that tension between something that looks timeless and something that is fundamentally temporary, between the slow patience of trees and the abrupt violence of volcanic rock, between the safety we like to imagine in a green landscape and the reality that it sits on top of one of the most active and complex volcanoes in New Zealand. If you were intrigued by how Mount Taranaki turns destruction into life, hit the like button and subscribe. Thanks for watching, and keep looking closer. Veil Origins: Impossible Truths.